model building using stepwise and hierarchical method. And then we actually did article summary on this using stepwise method. And hierarchical method quite often used in social science, particularly in psychology field based on the theory. So as you can see, stepwise method is more exploratory. Let's say you have 5 predictors and you want to find which ones are best predictors, significant predictors of the dependent variable, and remove unnecessary ones so that we can have a parsimonious, conservative model, right? And that's the stepwise method. We put them all in there, dump it into it, then a computer will tell you which one is the best predictor, second best, and third best, and insignificant ones. Then based on that, we build the model, that equation also. Hierarchical method, like we learned last week, it's based on something. Normally it's theory, or physiology. People have physiological mechanism that you all know. What's going to happen, step 1, 2, 3, right? Theory will say A will predict B, B will predict C, like that. And there is some tenets and emphasis in the theory. Or literature, conclusive literature. Exercise will be highly correlated with what? Positive emotions, conclusive, that we want to add something more to it, then it's based on the literature. That's the hierarchical method that we use. So stepwise method, we ask a computer to determine which is the best predictors. Hierarchical method, based on the theory, mechanism, or literature, researcher says this is the best predictor to begin with. I want to see adding 1 or 2 or 3 more, add more significance R square, whether it adds more explanation toward R square or not. And the researcher is controlling the process. Got it? That's the differences between those two. So utilizing, and I'm going to repeat multiple regression one more time with why we are clicking certain things, then stop right there and I'll give you time to digest it, then go on to stepwise and hierarchical, okay? So I'm gonna go multiple regression one more time so that you can remember, and then I bet all of you have been practicing it. Reset. I'm going to move. Okay, if you could, you can unmute yourself so that you can help me. All right, we are moving dependent variable, which is sales, album sale, to here. Then I'm gonna move all of them to here. Okay, so this is a multiple regression. I'm just simply doing it so that we can build upon it. Then statistics, R squared do not really need for multiple regression unless we do more model building, okay? But I'm gonna just click it because that's what textbook does, so I don't want you to get confused. I'm gonna just click all of them what textbook says so. And particularly collinearity diagnostic, this one tests your multicollinearity, okay? Confidence interval, you could get it from here, or more robust one using bootstrapping, okay? Then I'm gonna click it. And doubling Watson test, we don't do it because our data type is not really needed for this test, which is more related to the data, independent predictor that was collected like based on time sequence. Then it could be highly correlated, same one, first time, second time, third time, could be highly correlated, right? And then to ensure that one, first time, second time, third time collections are independent each other, that's the one assumption we need to click this, but our data is not like that. So that's why I'm not clicking. If you want to test the dependent variables error, the outliers, you can click this. But before you come to here, I want you to do outlier test utilizing what we have learned. You will see, you can identify a lot of other outliers beyond the dependent variable here only. Independent variable could have a problem too. So I want you to detect that, okay? So I'm not gonna click this because, oh yeah, I need to click this because we are doing multiple regression. And you could change this one 2 or 3. 3 is a default. Continue.
Dr.
Plots,
Kid,
yes.
so we could use that function to find outliers
For
the one you
dependent
just showed.
variable only.
Oh, okay.
Yeah, that's why I wanted to do also the regular outlier test for all continuous variable, okay? All right. Then So now I am, okay. Thank you, Michael. Interrupt me like that. Otherwise, I'm keep going, okay? Keep interrupting me. It's not interrupting me, asking me questions. So then we could do, using plot, we can do multiple tests here. This is a homogeneity test. So we put residual, standardized residual here, y-axis, and the standardized predictor here. Then if you click produce all partial plots, this one tests the linearity between one independent variable, that small, the scatter plots coming up because you clicked this. Then histogram normality, probability plots for dependent variable, you click this, then you will see the little PP plots and the histograms like that. Then continue. Then save, we save a lot of other stuff to test the influential cases. So first, from predicted value and residual, you do standardized because that's what we just clicked to do it, the plots. Then textbook somehow clicks this, and what is another one? But we don't really use it. So don't worry about it if you end up forgetting to click it. And it is too. I don't know why they're doing it. Then we want to do the case distance, all three of them, and test leverage test. We learned about that. And then standardized betas and standardized difference fits and the covariance ratio. Those are the all influence cases test. And then you continue. Then options, ensure that exclude as a missing. If you ever have a missing, you need to use list wide. Okay, that's the regression part. Otherwise, you could have a weird output. Then we don't touch style. We could do bootstrapping if we want to, or your data need that. Okay, but I'm not doing it. Then you paste it, then you will see whole program. So when I run it, that's the regression that we learned the last week. Whole output. Start with the regression correlation. You can detect the potentially multicorrelated here if any variables are highly correlated. I mean, textbook sometimes it says, I have it on my slide, 0.9, but if you even see 0.7, oh, I need to check VIF between these two. That's the sign for you to look at whether you have two predictors too highly correlated, okay? Then you report RA's correlation table for regression output. You start with the descriptive, correlation, regression output. That's the way to present it.
Dr.
Then,
Kim,
yes,
sorry.
That's okay.
If you scroll up a little bit more, right there. So if a value for the correlations, if it's above 0.7, that's when when there's multi-code. I can never say that word.
Multicollinearity. But though, it's not always. But if 0.7 is pretty high, so I would pay attention to those two variables in VIF test. When I see like a 0.6-ish, I do not worry much. If I start to see 0.6, depending on sample size again, here too, right?
Of course.
So if you see any high number, ensure that you check the VIF closely, okay? Then if a VIF is below 10, like 1, 2, 3, 4-ish, you don't have to worry about it. But let's say, although a criteria is 10, if it goes like 8, 9, then you have to scratch your head like, do I need both variables? Or can I make my model more conservative? You need to make that decision. Yeah. Okay, I am going down. Please interrupt me like that. Then here is one whole model. This is multiple regression. Now, R square is pretty strong, 67% round up, 67% explained by these three predictors. This is, I mean, dream for us, for my field. Then what is it? This much R square is significant. Significantly explaining. How do we know that? ANOVA table is right below. So when you see my example of how to report, you will see R square equals to what? Then F value there, that comes from ANOVA. ANOVA test what? Model, whether that model that we put together is significant or not. Yes, it is here. This is a p-value. F value is this high, which means this is a very strong, good model. And you will see here, the change statistics, R-score change, you don't have to worry about this part when you do multiple regression. But this one is the one that you will need to read when you are building the model using stepwise or hierarchical regression. So you report R-square along with ANOVA table here, alpha value, degree of freedom, and the p-value here. Then you go down, this is your regression, and utilizing unstandardized values, you develop your regression model. And when you are talking about how strong their relationship, you use standardized values right here, sounding like correlation, but it's not really correlation. But this is the way we can compare which one has a stronger relationship, stronger predictors, which one is a little less, as you can see here. But unstandardized one cannot give us that. That's why we use a standardized one to interpret the strength of the relationship, direction of relationships, okay? When you're interpreting it in the writing and you use a standardized one like a correlation coefficient, because this size tells you how strong that relationship is because it's standardized. Okay, so as you can see, advertisement budget and the number of plays on radio per week has a similar effect, but the attractiveness of a brand image, not really, but still significant, right? Yeah, that's the way you can see. Then VIF is right here. None of them are going over 10, not even near to 10. So you're just like, although there was a little high correlations between number of plays on radio and the album, say, oh, not that one, not among, nothing actually. Advertisement budget, album sale, that makes sense. No, I didn't have to worry about it. When you look at correlations here, look at the correlations between predictors to detect, to sense possible multicollinearity. Okay. All right. Then come up. Yeah, histogram that we clicked, relatively normal, as you can see, it doesn't. And then this is the homogeneity, right? If this one shows any pattern, then you need to be worried about the assumption, okay? But it's all split, and you don't see any pattern going like going down, going up, anything like that. It's just all spread. That's a good sign, okay? Linearity test afterward, relatively linearly related. That's a good sign. And so assumption met, the normality assumption met here, and that's it. That's end of it. Then influential case, because you clicked so many, as you can see, these all came out, right? So if you want to have a summary, then you can go analyze, report, case summary, again, as you have done it, then go all the way down. And whatever we want to look at is, I'm going to go all the way to, from here, this, leverage, ratio, and all the beta. Then you move them. Once again, I want to see all of them. So our sample size is 200, okay? Ensure that you have 200. If your sample size is 300 or something, then you need to put the number. Then if you say paste, then you will have a program. If I say okay, then I see this, right? So what's the best way to detect this? Move this one into where? Excel sheets, so that you can do the ascending, descending to see anything, any one of these cases violates criteria. Okay, so how do we determine table, which is in slide number 16? 16 is influential cases, then assumption test is on 18. That's the table that you want to have always handy. Okay, that's the multiple regression. Questions so far? So now it's going with your understanding, and you can see what's going on and clarifying things, right? Yeah. Any questions so far? So you could use this method, exactly same method, practice it with this data because you have annotated output, learn it, then apply same skill, transfer that to your stat6 and do exactly the same way. However, the data, the stat6 is not clean. So you need to do each step, you need to adjust the things a little bit, okay? All right, questions so far before we go to stepwise? All right, stepwise and hierarchical, you will see much simpler since you learned this whole thing. I'm gonna get rid of this whole thing. Okay, now I am going back. So I did influential case test, all good. Multiple regression helped me to clean up the data. Now analyze, now I'm going stepwise, okay? Analyze, regression, and linear. Go ahead, you go ahead. And I'm gonna reset it. Then what I'm clicking here has exact picture on lecture slide I just added this morning. Okay, so are you there with me? All right, so now I'm going to move. Again, dependent variable there. Then independent variable predictors, the same place like a multiple regression. So here, this is the difference. Multiple regression, we did not touch method here. Now we are saying, okay, do stepwise. Oh, what's the differences between backward and forward? I have FYI there, and stepwise is good enough to use it, okay? So I changed the method to stepwise, then statistics, we click, of course, R-square change now, okay? We want to see how one goes in, second one goes in, and then how R-square changes and whether the change is significant enough statistically. That's what we're checking. That's the only difference is. Descriptive parts and collinearity, you can check it. If you already checked them all from multiple regression, now you're doing it stepwise. You don't have to. If you want to get confidence interval from here, click it here. If not, you can use it through bootstrapping. Case diagnostic, we already did it from multiple regression. If you haven't done it though, through multiple regression, you may want to check it out. So you need to click it, but I'm not gonna click it, then continue. Then plus, we don't have to do it. We already checked through multiple regression, so I pass it. Save all this, we already checked them, so I don't have to do it. But if you have not done it through multiple regression, it's stepwise, it's straightforward your analysis, then you need to do the same procedures. Then options, this is a change here. Option, ensure that you have used probability of F, okay? Then here, we are going to change the number slightly. The reason that we are changing this, the p-values here, we are doing multiple tests of stepwise. One go in with probability of 5% of making type 1 error. Another one will go in, we do the same thing. Third goes in. So each time the possibility of making error for type 1 error that inflates. To minimize that problem, we're changing this one to 105 and 0.01 so that we don't inflate the possibility of making type 1 error. Then include a constant in equation, clicked. And of course, if you have a missing, we need to use list wide. Then say continue. That's the only difference is in stepwise, okay? Then paste it. So please do it, paste it, I'll wait. So that you have a program. Once you have a program, I'm going to run it. It's a much shorter output. Are you ready? So run it. I'm gonna run it too. I'm gonna just say, okay. All right, so correlation comes out again, same table as we have done, but you will see some differences here. Like first enter the first one, highest, like the most significant predictor, second significant predictor, third. So you can see the number of plays on radio, it should not be. Let's see how it comes out on the bottom. Here, total, so model summary here. R square, first one entered, then R square was 0.36, 36%. second one entered, then it becomes 63%. That increase from first one was significantly predicting here, okay? Significantly predicting dependent variable. When we added a second one, R-square change was this much and statistically significant. So we are using it. Third one, when we added, it went up slightly. R-square change was 0.035, but still statistically significant, means it's adding significance toward R-square total. So means all three of them are predicting it. Then you're using all of them. This is ideal, but normally it doesn't come out like that. When you have like 4 or 5 predictors, you will come up 1 or 2 statistically insignificant here, like 4 or 5 here with p-value higher than 0.05. Then you end up removing those out of your formula and use only the significant ones so that you can make your model predicting regression model conservative. So putting least amount in it, cost, then getting the best outcome. That's what exactly we're doing here.
Dr. Kim?
Yes.
So
all right, and then go to, yeah, output. So correlation, then so 1, 2, 3, each one enters all significant. So here is important, okay? So here you see ANOVA also step 1, step 2, step 3. If you end up using step 3, so which means all of them, then you report this ANOVA table. Got it? However, some analysis you may have, let's say hypothetically, step 2 significant and step 3 was not significant. So you decided to remove third predictor. Okay? If that's the case, then you read step 2 ANOVA table to report. That's the only difference is. When we do multiple regression, it just gives you one ANOVA table. But for stepwise, each item goes in, each predictor goes in, and every single time you will have an ANOVA table. Whatever you decide up here, what steps you're stepping right there. You get it? Then same thing, go down, look at this. This is a regression table. When we enter the 1, step 1. When we enter the second one, 2, step 3. Oh, so we are going to use step 3 ANOVA, then step 3 regression coefficient right there. Hierarchical now. So hierarchical, researcher is telling computer what to do, not automatically put in based on the numbers, okay? So I am going again, same. I want you to do the same. Follow with me, and then I'm going to reset here. Okay. So dependent variable sale again goes in. Now, first predictor for the album sale is advertisement budget. How much money you put for the marketing, right? That's for sure, number 1. But the researcher wants to know whether adding number of plays on radio and attractiveness of that image they're putting, adding those two, how much does it add in R-square? That's what they want to know. So clearly, based on their practice, they know advertising budget is the predictor, but want to know 2 additional one, adding it, whether that is significantly adding predictability. That's what researcher wants to know. So she wants to control. So okay, first, album sale, advertisement budget, that's the first model. Let me have another model adding 2 more. Then you click where? Next. Do you see that? The next? Next. I want to add now number of play on radio and attractiveness on the brand. Or you can separate them. I want to see one at a time. Researcher decided. Okay, but you're deciding which one goes first, which one is next. So I want to see both of them together at the same time. So I added next. And in previous, as you can see, I have a first one based on my marketing practice. This is the predictor. Next one, I want to see how much this one is adding to it. In our field, in psychology, we do that. Personality predict their behavior. I want to know whether environment is also adding more to it, then we can do hierarchical right there. Or we could do environment first, then see whether personality factors adding more predictability there. You decided that order as a researcher based on the literature and the theoretical tenets. Then statistics, click same thing. R-square change is the most important, and other ones is the same thing that as we have then. You decide which one you want to click and continue. Okay, I'm not gonna go too fast. All right, you're coming, yeah, are you with me? Plots, I undo it because I already explored all that through multiple regression. So I will just continue. Save, I unclick any one of this because I already have done it. So I'll just continue. We don't have to worry about changing this because it's a hierarchical, it's a different mechanism. So you just continue and you paste it. So it was very quick. It says, and then keep that enter there too. You don't have to change it. All you need to change is the next, like this button. You're controlling one after the other, all right? Then when I say okay, and you will paste so that you have a program. Descriptive again, correlation table, exactly same thing because we've been playing with the same data. First entered, second entered. Only 2 levels I did. We could do 3 levels depending on my understanding of the area field. So model summary here, when we enter the first, it explains what? 34% R square right here. And then it's a significant, that's good. Oh no, it's a significant right here. I need to come down, I'm sorry. Come down, ANOVA. Oh yeah, it's a significant model. Now I wanna see when we added 2 more to it, whether it's really significantly adding predictability. And look, it jumped from 0.34 to 0.67. That R square change was this much and statistically significant. So now I found a new model. I used to only consider that budget to predict my sale, album sale. Now adding 2 more, predictability jumped up from 34% to 67. That's huge. You know what? I'm gonna go with this model. Then you use ANOVA second one. You see that? Because it's a new model, adding 2 more. Then regression, first one, second one. So you use second one because it's all significant. And then that's the hierarchical regression. Only differences is who is controlling that order of it. Stepwise, a computer does it based on the numbers, quantitative numbers. And hierarchical, I decide based on the concept and theories and practices and or mechanisms, whatever we have justification. Okay, so that is a hierarchical regression. And when you're reporting again, if you end up doing second one, then you decide second end of a table, then also second one here using this output. Let me show you one thing though, so that you understand where they're coming from. Many times, so this is a table where they had 3 steps of hierarchical regression. Okay, so first step, they added 3 variables to predict their VO to max. Then second step, researchers added weights to it to see how much weight actually add more explanation predictability. Third step, they added heart rate. So they have 3 steps doing, I mean, it could be more, 4 or 5 times, depending on your research design. Then you see, they have unstandardized, standardized, model 1, unstandardized, standardized from model to second step, adding the weight right there. Third model, adding heart rate, they're reporting all of them. R squares of all 3 of them, and so that you can change, you can see the improvement from about 20%, 43%, and 71% as they're adding one after the other. Then do you see that F value? Where do you think this one is coming from?
ANOVA.
Exactly, ANOVA. First, second, and third. This one can be good summary table for hierarchical. Then R square change from first, second, and third. Then R square change has p-values right there, right? With F values. That is what they're reporting. That's the table. So where this one F is coming from, let me go back. Output. What is that? Oh, this is only 2. So it's F right there. Yeah. F values right there. Degree of freedom and P values right there for this one. So this little the little triangle means it's increase, changes, increase of R squared, increase of, or changes of F values. So that's the way they summarize this whole thing. So when we read articles, it looks like, oh yeah, there's a numbers, but can you see this whole thing coming from how many outputs to make it this simple? That's the hierarchical regression. Okay, so we finish it. All right. So this is it for multiple regression, simple regression, then model developing hierarchical and stepwise. Very, very strong tool for all subfield in kinesiology. Stat6. Oh, which one should I use for Stat6? Multiple regression, stepwise, and or hierarchical? You decided based on your understanding of this field, the personal trainer. I have seen, like I said, a number of you, I have seen one student actually did hierarchical regression with this last year. It was beautifully justified. And many of them did multiple regression simply. This data, like I told you, it's not clean data at all. It's a real data. So you will see that there are a lot of large ones that you will need to remove, and assumptions are all violated. That is the real data also. So then you remove unnecessary and with justification again, okay? Then you will see the data becomes more homogeneous and cleaner, normally distributed like that. And that's the process that I want to go through. And we've been building from week 2 all the way until now for this data, okay? When you do the outlier test, you will see the problems right there. When you see the descriptive stats of 231, I believe, yeah, then you will see some problems right there. You will detect it. It's your data. When you look at it with just min, max even, descriptive stats with the 231, do it. And in age, you will see some problems there too. I mean, there are some people, no income even. Is that part of your data? Do I have to keep it? You will see 12 years old one, 13 years old one, 14 years old one. Can they be personal trainer and part of this data? Yeah, right. So those are the ones that you need to gauge through, and then those are the ones pop out as outliers. And the highest paid person also pop out as an outlier too. Then is it possible to get paid at that level if they have that much of experience? Then common sense. Oh, yeah, it's possible. Then I'm keeping it. But zero salary, is it worthwhile to keep it there? Who are they? They're working hours and not getting paid. Who are they from your understanding? There are personal trainer settings and they filled out questionnaire. They're not getting paid, but they're there. Who are they? Anyone is doing personal training? Do you have like anyone doing the work but not paid?
Interns.
Yes. Exactly, interns. Then do you want to keep them in the data? Is that about the interns or about the personal trainers? Here we go. So a lot of thinking that needs to go in. Never been clean data and clean like a click, 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 and you have output, then you just finish it. Never happens like that, believe me. So, oh, I have zero income. Who are they? Oh, interns. Do I have to keep them? Okay, so that's why I'm keep telling you, work as a group and then have this conversation. That's the true conversation that even researchers are having live time. Like, I have this problem. What am I supposed to do? Then we chat, we decide with justification. And then that's what I want you to practice with this data, okay? So first one, identify IVDV regression model. So you need to have the regression model, multiple regression model. Then conduct the descriptive stats and correlation. That was basically step 5. Now you're doing it one question because it's been building up that way. Then run multiple regression and write up the regression model using estimate, describe regression results, and present them in a table. So find how to present those table. I have them too. And then I ask you a whole lot about this. So you could start with the number 5 or you could start from number 1. It's up to you. I don't care how you present it as long as you show me your logical process of doing it. And then at the end, you make a conclusion out of it related to research question. These are the assumption tests that you need to do. Then when you're reporting correlation, you just report that correlation comes out with the regression. You don't have to run separately and then running separate assumptions for regression, for correlation. No, you don't have to. You don't have to focus on the assumption test of what? Regression. Since we're doing advanced assumptions overriding the correlation. Correlation, when it comes to correlation and regression is much more robust one. And because of that, we're doing all this assumption test. So whatever the correlation has assumption, if regression meets all the assumptions, overrides correlation stuff. So you don't have to worry about correlation, like separately testing it. No, regression already doing it. Don't worry about it. Yeah. All right. Any other questions? So I would say the outlier test and assumption test and the influential case test and assumption test happening at the same time. It's not like a step by step. So you will see the outlier test and the influential test is you do it and you remove some outliers with the justifications, then your assumption gets better, particularly distribution. Homogeneity gets better. Okay, so what I would do, general outlier test to explore my data to ensure my data is healthy enough. Then the influential case with that case outlier test in the regression, and then see what's going on there. And then if you want to remove right away, or knowing that you have outliers, and then do some assumption test at the same time. And then assumption also comes out crazy, which will be, then you get rid of those potential outliers and do again the assumption test to see where assumptions are cleaner. So a lot of things happens at the same time to adjust to like best. It's not like step by step. It's simultaneously happening to make a best decision. The album say, okay, syntax. Do you see my stat6 syntax here? This is mine. So when I was looking at it, I just did a first regression without even doing any the test. Then I found after regular linear regression, I see too many problems in cases of normality, homogeneity, multicollinearity. I ran Explorer to inspect outliers and normality. So I went back to the basic ones because I saw too much problem. So that's what I did. Then I make a note because of this and that. I made what decision. Then I go with the descriptive to see the field for my data. Then I go again. I remove the sum. Okay. Then I go regression again. Then the multicollinearity issue is improved, blah, blah, blah. And final data, I do the regression and summary. This is my last one. Then I did bootstrapping so that I can get robust, confidence interval. It looks very simple, but in the process, there were a lot of decision made already. Okay, so that's something that you can do, like start with something. You can start with the question number 5. You can start with a simple regression right away and then detect a problem, adjust until you have your final clean data to run your stats. It's either hierarchical or multiple regression or stepwise. Okay. All right. So let me go to questions again. Okay. For question number 5, you can make a bullet points. Outlier test. This is what I did. This is what I found. This is what I made a decision. Then influential cases, Cook's distance criteria was this, and none of them went over 1. And leverage criteria was this based on this calculation. I haven't seen anything, blah, blah, just bullet points. And then the difference beta, you don't have to do this, difference fit. Beta, none of them went over 1. If you want to see it, this one, same thing. None of them went over 1. So that's what you need to just bullet point it. And these are what? Assumption test. That linearity, normality over error, it comes out with that same click that we did. Homogeneity and multicollinearity, VIF. I help you to the directions so that you can make a better decision. You could do exactly the same analysis as a group, but interpretation could be different. So individual paper should not look exactly the same. If you made a collective decision, you can say as a collective, as a group, we decided to move this because of this reason, fine with me, because we publish paper as a group. So absolutely fine. But if it's like identical without explanation and you act like this is individual paper, then doesn't make sense to me.